One of the advantages of a closed loop control system is that um, the sensitivity to parameter variations is lower in a closed loop control system. What do I mean by that? So, in a control system, as you're using the control system, because of wear and tear, the gain of your control system is going to reduce over time. Okay, there will be some change in the parameters. The gain will change, reduce over time. And as this happens, you don't want the performance of the control system to change. You want the sensitivity. You want, for as the parameter varies, you don't want the output input to change very much. And in a closed loop control system, because of the feedback, the output does not change. Let's take a look at that. So we've looked at this control system and we've looked at the error in the control system, which is given by this equation. Okay. Now, let's assume that there is no disturbance and no noise. Let's just ignore those factors for now. In that case, the error is equal to this equation here. Now, let's say the process over a period of time, because of wear and tear, the process transfer function changes from g to g plus delta g. Okay, so there is a small change in the process transfer function. So what is the error going to become? Now you can substitute g plus delta g instead of g here, as I've done here, and then you can evaluate delta E. What is going to be the change in error as delta G changes? Okay, and you get this equation, and you can, if you assume that this term here, GC times delta G, is much less than GC times G, which should be true, right? Because let's assume that the change is very small, delta G is smaller than G. In that case, you could write delta E like this. So basically, delta E is proportional to delta G, but then there is a 1 plus GC times G square term here, which shows that uh, a small change in the transfer function of the process is going to change the error by a much smaller factor. Okay, because we've already seen that we are assuming that delta G is much smaller than G. Okay, now of course you could do a little bit more simplification, and if you assume that GCG is much higher than 1, then you can write an approximation like this, and you can see you get an equation like this, which means uh, the 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 effect of the change in the process on the error is going to depend on the loop gain. If the loop gain is higher, the sensitivity of the error to the parameter change is going to be lower, right? A larger loop gain results in smaller changes in tracking error. So that's the advantage of having a large loop gain in your control system. This large loop gain essentially compensates for any changes in the process. Now we quantify these changes by using a parameter called system sensitivity. System sensitivity is defined as the ratio of the percentage change in the transfer function to the percentage change in the process transfer function. So TS is the overall transfer function of the closed loop system, and G is the uh, change in the transfer function of the process. And sensitivity is given by delta T over T by delta G over G. Okay, and you can evaluate that. When the changes are very, very small, instead of using delta T, you can use differentials, and you could say dt over T over dg over g. Uh, if you have an open loop system, and I will leave you to prove this, the sensitivity becomes equal to 1. And if you have a closed loop control system, what you would see is that that the sensitivity becomes 1 over 1 plus the loop gain. So if the loop gain is very high, the sensitivity is very low, and therefore the system is more tolerant of changes of the process transfer function. Okay, and this is what I have shown here. So in the closed loop, the sensitivity is much lower than in the open loop system. So one of the advantages of a closed loop control system is that uh, as the so the so the error or the output does not depend so much on the parameters that you're using in the transfer function. Okay, it becomes invariant of the transfer function. And one of the examples that you have seen, okay, I don't have that in the slide, is an op amp, right? So when you make an op amp amplifier, okay, the op amp has got an infinite gain, right? So uh, of course you know that in real op amps the gain is not going to be infinite, but it's going to be very high. And as you put one op amp versus another op amp, the gains might be slightly different, but the gain of the amplifier does not depend on the amplifier of the op amp at all. That is because the sensitivity to the variation of the op amp differential gain itself is very low.